Greetings. We're from the Florida Institute of Technology, and we're here to present our project, the Train Probabilistic Models for the NAO robot in a Labyrinth. My name is Sam.
My name is Sagar.
My name is Cleanthus.
I'm Neda.
Akram.
I'm Gorwal.
My name is Ron.
The project we're presenting is focused on the NAO robot. Primarily, we use the proximity sensors located in the left and right chest regions and the cameras, which are located in the mouth and forehead region. The goal is to make a high-level utility-driven artificial intelligence support for the movement of NAO. This would enable users to specify the tasks in terms of utility rather than having unique code for each small task.
This research, the goal is improving the performance of extended Kalman filter based on the simultaneous localization and mapping. And one of the most important approach in this research is that now as a humanoid robot is addressing the problem of slam in a room, which has multiple landmarks with random locations and navigate the instruction by using AR or augmented reality. For achieving an enhanced positioning system, they implement iPhone onboard gyroscope sensor, which is used for motion control. Next slide, please. The second one is indoor robot navigation using POMDP based on Wi-Fi and ultrasound observation, which is present an algorithm based on SLAM that they call Wi-Fi simultaneous localization and mapping, or WSLAM. This algorithm can learn the observation and transition matrix in autonomous mode, which is coming from WSLAM, and this system is useful to navigate in indoor environment with a real robot. Next slide. A POMDP-based multimodal interaction system using a humanoid robot is the third paper we consider, and they suggested a multimodal interaction system between human and robot by expanded framework of POMDP to represent uncertain state of Markov decision process as a stochastic state in another humanoid robot named Pepper. The interaction system consists of two layers. Firstly, the decision to start interaction based on the physical distance between Pepper and the user, and secondly, that is control multimodal interaction. The last paper is variable resolution decomposition for robotic navigation under a POMDP framework, a variable resolution technique for reducing the complexity or state space of the POMDP. And they consider the ability of robot to navigate a specific goal location in an environment. It is required for the robot to keep an internal representation of the environment, usually in the form of a map. So this is accomplished by automatically adjusting the number of states in the grid base while maintaining the level of detail required for the planning at given region to find efficient policy.
So here are some background about Bayesian network. Bayesian network is a graphical probabilistic model that consists of nodes and edges. And the node represents a random set of variables, and an edge represents conditional dependencies among the nodes. The value of variables could be either discrete or continuous, and the variable in the Bayesian network consists of three types: observable, hidden, and evidence. The graph of the Bayesian network is acyclic, which means nodes have direct influence over another. It represents a joint probability distribution of the variables, and conditional probability table is associated with every node. And the main goal of the Bayesian network is to perform probability computation and be able to conduct inference in the environment where knowledge is uncertain. There are two types of inference in the Bayesian network: exact and approximate. So here's another background about the dynamic Bayesian network. Dynamic Bayesian network is a special version of the Bayesian network. It represents a probabilistic temporal model. Dynamic Bayesian network is constructive within a domain that evolved instantly, like robot movement, in which time plays a role in addition to uncertainty. The graph in DPN is composed of sequence of time steps or slices. As you can see in the graph to the right here, t-1, t, and t+1. Each sequence consists of random variables, state variable x, and evidence variable e. Three paths that construct a sequence in dynamic Bayesian network: prior state variable, transition model, and sensor model. Each variable in a time step influences other variables in the next time step, and so forth. In addition, each time step has a distinct copy of random variable, and the value of a variable in time step t+1 is computed by the same variable in the previous time step.
So about the POMDPs, which stand for the Partially Observable Markov Decision Process. It's a framework for modeling dynamic and uncertain environments. Adding rewards associated to the states and the transitions in the dynamic Bayesian networks. So a POMDP is defined by a set of states, a set of possible observations, a set of actions, a transition probability functions between states reputations, observation conditional probabilities, an initial belief, a discount factor, and the rewards associated to the states. Next, please. Through the observation of the evidence, the robot will update the probability distribution of its current state. It's like an initial belief. So in order to optimize its choice of the next action, maximizing the future rewards, actions at a time step contribute in the next state transitions. Rewards represents the benefit of the state. The typical goal for the reasoning in the POMDP is to generate the optimal policy, which maximizes the amount of the future rewards. The belief is the probability distribution over states. The robot will optimize the next action, making decisions based on the current belief.
So for the NAO database structure, it was basically a compilation of all the measurements from the sensor data and transition data, and also contained the code from which we used to calculate said measurements. Also, it also contains the CPTs and transitional probabilities that were calculated. The NAO robot sensors consist of the left and right sonar and the visual sensor and the head of the robot. The sonars are used for detecting objects, and the visual sensor is used for detecting standardized landmarks on the walls of the labyrinth. The transition data for the NAO robot was taken when the robot was placed in the middle of a cell and was asked to go to the adjacent sides of the cell. Next, please. With this data, the recorded position, the robot was given a position to go, and then the final position was recorded. This data was organized into a 4-column data sheet, which was the given action, the given position, the given orientation, the recorded position, and the recorded orientation. This data was used to calculate our transitional probabilities. The sonars were very important to being able to localize the NAO robots, as it helped us to calculate the distance between the robots and obstacles ahead of the robot. All the sensor data from the robots were compiled into a 12-column data sheet, as seen in the example data sheet below.
As you can see, we use 2 different implementations for the belief network due to the landmark node. The first implementation, shown in figure 3, is where we have one landmark node for all landmarks that we're going to detect. That way, if at least one landmark is detected, it would come back true. In the figure 4, we have the second implementation, which is a single node per landmark. For every landmark we're trying to identify, it has its own node, which will specify true or false if that landmark has been identified. The location or position node is the M unique XY coordinate positions in the labyrinth, as shown to the right, which is 32 unique coordinate positions. The angle node is the angle between the robot's head and the torso. From 0 to 365 degrees, we used 11.25 degree steps, creating 32 unique degree angles. The left sonar node uses the left sonar values based on the XY coordinate position and the angle specified earlier. The CPT table size was the number of XY coordinate positions by the number of angles by the number of sonar values, which is 0 to 2.95, creating 296 options for the sonar values. The right sonar node is the same conditional probability table. In our data, you'll only see 196 sonar values for the right table due to noise issues. The landmark node determines if the specified landmark is identified. As specified on the previous slide, we're going to use the second implementation of the belief network, creating one landmark node per landmark to identify. As you can see in the image to the right, there we use 3 primary landmarks, starting at the initial position, left and right of the robot, and behind the robot, creating a conditional probability table size of 3072.
Before we could implement our proposed belief network, we first needed to compute the conditional probability tables necessary from the database. So in order to do so, we implemented a sensor fusion model for our belief network. The model reads the data and checks how frequently a given sonar value was recorded at any given position and angle in the labyrinth. Different nodes may have different parents in the network, therefore the size of the CPTs may differ based on its parent and the type of sensor data. The conditional probability tables were calculated for the left sonar node, the right sonar node, the landmark, and for the state transitions. The recorded data for sonar node is distance in meters, and the range of the recorded distance measurements in the database is 0 to 2.95 meters for the left sonar node and 0 to 1.97 meters for the right sonar node. Size of the CPTs that we calculate depends on this range. What you see here is a section of the conditional probability table for the left sonar node. Both the sonar nodes have the location node as their only parent. And the first 3 columns on the left are all the possible values of the location, that is the position and different heading angles in the labyrinth. And all the subsequent columns are probabilities of certain sonar value being detected. The landmark data was recorded with 3 pair of NAO markers placed around the robot at head level on 3 different walls. It is worth noting that the NAO sometimes fails to detect landmarks, or sometimes it detects but interprets the NAO markers wrongly. Since the visual data is recorded by the camera on NAO's head, the landmark detection is specific to NAO's position and the sum of its head and torso angle. The first 3 columns on the left are the recorded positions and angles, and the subsequent columns are the probabilities of detection of the respective NAO markers. The table on the right is an alternative approach where only probabilities for detection of the landmark is used. The data for transition available was recorded for a pair of action commands. One action command for change in state and the other action command for change in the heading angle. And the resulting state and orientations were recorded at the end. The start positions for all the transitions was always taken to be 4, which is in the center of the state matrix. And the heading angle at the beginning is always 0. So what you see here is an illustration of the transition probability table. So this is the entire table. The leftmost column here represents the action commands that were given to the robot by the user to perform. And the subsequent columns are the probabilities of the positions and the orientation that now ended up in.
Particle filtering is used to infer the current location of the robot given the evidence. So the way it works is we apply the likelihood weighting sampling algorithm to the dynamic Bayesian network, and from those samples we use the ones with a high probability, the ones that have a high weight, in order to generate the new sampling distribution. So it comes from a multivariate Gaussian mixture, and the weights are given from the previous samples. We also apply multivariate interpolation to obtain that sampling distribution. So our research plan was to create an interface for all the functions and all the functionality that we mentioned previously. So firstly, we wanted functions that were able to calculate to compute the conditional probability tables given a structure of the Bayesian network and also a measurements file. And also we wanted to have a function to perform exact inferencing on the Bayesian network. And lastly, we also wanted to have a likelihood weighting algorithm both for the stationary Bayesian network and for the dynamic Bayesian network to be used with the particle filtering algorithm. So our first function is the one that estimates the conditional probability tables. It accepts a structure format of the Bayesian network, and also a file with all of the measurements. So the structure of the structure file is seen in the figure to the right, where we have the nodes with all the node names and all of the parameters which every node takes. Then the connections between the nodes. So every node will have its parents in that section. And lastly, the parameters and each possible value that the parameters can take. In this case, we assumed that we implemented discrete Bayesian network and not continuous ones. So we need a list of possible values for each parameter. This function returns a JSON structure of the CPTs. So it will contain all of the multidimensional conditional probability tables of each node inside the Bayesian network. The next function returns a distribution of the current location belief given the sensor data. So in this case, our sensor data is the left sonar, the right sonar, all of the landmarks that are detected, and also the angle of the body torso angle. So this function performs exact inferencing and calculates the distribution, a normalized distribution of the current location of the robot. Lastly, the likelihood weighting algorithm accepts the CPTs of a dynamic Bayesian network, the query variables that the user wants to obtain the distribution of, the evidence variables, and the number of samples that are going to be used. The higher the number of samples, the higher the accuracy, but also the higher the computational time. The distribution is also normalized in this case. So the goal would be to have the distribution of the likelihood weighting approach be identical or close to the one of the exact inferencing.
So this experiment will illustrate the quality of the obtained model and observe the behavior of the NAO in the Labyrinth. So first we have the sensor measurement, where data are collecting from the environment, and the NAO is making rotation of 360 degree based on the basis of 10 degree and 5 degree. So when the rotation is based on 10 degree, the end location is almost close to the initial location. However, the landmark detection rate is about 50%. On the other hand, when the rotation is based on the 5 degree, the landmark detection rate is higher, about 70%. So we can see that when the rotation is the degree of rotation is smaller, we can see a better result when moving. Next slide, please. So here for the second experiment that is related to transition data, the robot mission is to walk in some direction in the labyrinth. The diagram illustrates actually the starting location, which is cell 1, 5th column, 5th row, all the way to the end location, which is cell 3, 5th column, and 5th row. And the initial orientation is straight, which is 0 actually. The walk is a sequence of steps, and each one is 2 inches. And at some point along the path, a rotation is made, and that rotation is based on 10 degree, 10 angle. While walking, now should record the reading of the surrounding, eventually check the end location and end orientation as illustrated in the next table, please. So as you can see here, always the initial orientation and the initial location are the same from the beginning, but the difference in the end orientation and end location. Sometimes after the rotation, we can see drift along either right or left. As we can see in the first round here, the end orientation is 12R, which is the NAO robot is facing, or he's turning a little bit to the right 12 degree at the end. For the second one, we can see that it's almost straight, 1 degree to the left. And all around in similar method actually.
We generated the sample results from the NAO robot into CSV files. Then we used Python 2.7 and 3.4 to parse these CSV files and generate the conditional probability tables. These conditional probability tables were written to new CSV files. All the code and the CSV files can be found in the repo for reference.
So the first example of our code being run shows, compares the exact inferencing algorithm and the likelihood weighting sampling for the stationary Bayesian networks. So in the left pictures, we see the exact inferencing algorithm given the sonar left and sonar right being 0.3 and 0.4. There are no landmarks detected and there is an angle of 30 degrees. And as we see, location 2.2 has a 50% chance that that is the actual location. And on the right side, we obtain the similar result with the likelihood weighting approach, where again, we see that position 2.2 is 0.5, 50% probability that the robot is located in position 2.2. The second example shows the running experiment of the dynamic likelihood weighting approach, where the initial position distribution is seen in the left picture, where again, the robot has a 56.9% chance of being in location 2.2. And then after we apply the actions right and right, having started from 2.2, we obtain the probability that 98% the robot is located in location 3.4.
So here's the heat map for the better visualize for the transition probabilities and likelihood weighting. So for the first picture on the left is the samples of the likelihood weighting. So you can see the color from dark blue to orange. So it's the probability from small value to the high value. And the central one is the orientation transition probabilities. It shows the actions that user gave to the robot and the recorded position that's in the result. Same as the third one. You can see the Y coordinate is the action that user gave, and the X coordinate is the recorded as the result.
In conclusion, we found the NAO robot's actions are proven to be non-deterministic. The POM-DP DDN is proposed so that we can model the NAO movement, and using the sample usage of the model and a likelihood weighting based location inference is offered as a guide to using our results. Thank you for listening to our presentation. Any questions?
Okay.